Hello, class, and welcome to Chapter 3, Section 3 on solving conversion problems. This chapter and section can be a little confusing in chemistry, so I would encourage you. I put 2 worksheets in this week's module, and I provide answer keys to those worksheets. So please work through those worksheets, make sure you understand them, how you got the answers, so that you're well prepared for the test, which will be on all of Chapter 3 at the end of this week. I will also try to post another YouTube video that describes this in a little more detail as well. But if you can work through those practice worksheets and understand those questions and understand your discussion for this week and help each other with that, you should be well prepared for this topic in the test. So when we're solving conversion problems, we first need to talk about conversion factors. And a conversion factor is a ratio of equivalent measurements. So for example, here is our conversion factor. 100 centimeters is equal to 1 meter, and that's our conversion factor. We can flip it around and say that 1 meter is equal to 100 centimeters. So our conversion factor is a ratio of equivalent measurements. The measurement in the numerator is always equivalent to the measure in the denominator. So for example, if you have 100 centimeters, that is equal to 1 meter. And if you have 1 meter, that is equal to 100 centimeters. Having our conversion factor is important for solving future conversion problems. The conversion factors below are read as 100 centimeters per meter and 1 meter per 100 centimeters. Another look at this is to just making sure we're understanding that the smaller number is usually the larger unit. So this is what 1 meter looks like. You guys are aware of what a meter stick looks like, and there are 100 centimeters in that 1 meter. So all the time in a conversion factor, usually the smaller number is the larger unit, and the larger number is the smaller unit. In this situation, in this example, 1 meter is equal to 100 centimeters because a centimeter is a much smaller unit than a meter, and we need 100 centimeters to fill up 1 meter. The smaller number is part of the measurement with the larger unit, and the larger number is part of the measurement with the smaller unit. When a measurement is multiplied by a conversion factor, the numerical value is generally changed, but the actual size of the quantity measured remains the same. And we'll talk about and go over examples of that. In dimensional analysis, it's a way to analyze and solve problems using the units or dimensions of the measurement. That's why we call it dimensional analysis. So let's go through a sample problem using dimensional analysis. How many seconds are in a workday that lasts exactly 8 hours? We'll first analyze, then calculate, and we'll evaluate this problem. Let's list the knowns and unknowns. So to convert time in hours to time in seconds, you'll need 2 conversion factors, because first you must convert hours to minutes, H to minutes, and then you must convert minutes to seconds. So we need 2 conversion factors. And we must first identify those proper conversion factors based on relationships that 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. So those are our knowns, but we need to create our conversion factors based on that. So our knowns are that 1 hour is equal to 60 minutes and 1 minute is equal to 60 seconds. And the unknowns that we need to solve for, we're trying to figure out, we want to know how many seconds are in 8 hours. So we'll solve for the unknown using the conversion factors and setting them up so that the desired units will cancel, and then we'll multiply the time worked by the conversion factors. So let's set this up for us. 8 hours times our conversion factor, our first conversion factor of 60 minutes per 1 hour. And we always need to set up the ratio so that the units will cancel. meaning that the numerator, hour over here, needs to cancel with a denominator for our first conversion unit. So we know that those units will cancel, so we've set up the conversion factor correctly. Then we multiply by our second conversion factor. We said at the beginning we'll need two conversion factors. Do you remember our second conversion factor was 60 seconds per 1 minute? And again, we're setting it up so that the minutes will cancel and we're always left with seconds, which is our unknown value that we're trying to solve for. And we get 28,000 seconds in 1 8-hour workday. Before you can do the actual arithmetic, it's a good idea to make sure that the units cancel that we talked about and that the numerator and denominator of each conversion factor are equal to each other. So we got our answer, 28,000 seconds, and then we know that we want to have, so we then convert it to scientific notation, 2.8. I think this is a typo right here. This should just be 2.8000 times 10 to the 4th seconds, changing 28,000 into scientific notation. And I apologize for that. There's a little typo. This should be 2.8 times 10 to the 4th seconds. Then we evaluate, does the result make sense? The answer has the desired units of seconds, and since the second is a small unit of time, we should expect a very large number of seconds in 8 hours. And the answer is exact since you're given measurement and each of the conversion factors is exact. So it does make sense. Let's go over another sample problem using dimensional analysis. So the directions for an experiment ask each student to measure 1.84 grams of copper wire, and the only copper wire available is a spool with a mass of 50 grams. How many students can do the experiment before the copper runs out? Let's use our analyze, calculate, and evaluate steps. So let's first list our knowns and unknowns. From the known mass of copper, we can use an appropriate conversion factor to calculate the number of students that can do the experiment. And the desired conversion is the mass of copper to the number of students. So the mass of copper available, we know, is 50 grams of copper. And we know that each student needs 1.84 grams of copper. And the unknown is calculating out how many students can do the experiment. Let's solve for the unknown using our conversion factor and then solve for the number of students. So we know we have 50 grams of copper. We want to multiply by our conversion unit, making sure that the units cancel each other out. So we're going to make sure we have in our conversion factor, we want the grams to be on the denominator here. So we'll put 1 student per 1.84 grams to making sure that those grams of copper cancel out and we're left with what we want, the number of students. So doing 50 times 1 divided by 1.84, we're left with 27.174 students. And we have 27.174 people? No, so we have to round down to just 27 students. As the number of students, unfortunately, you guys cannot be a fractional number, so we'll round down to our whole number. Does the result make sense? The answer has our desired unit, students, and you can make the approximation that 1 student would use about 2 grams of copper because that's close to the conversion unit. So when you take 50 grams and divide them by 2, your answer is 25, which is close to 27. Dimensional analysis is a powerful tool for solving conversion problems in which a measurement with 1 unit is changed to an equivalent measurement of another unit. Let's go through another sample problem converting between metric units. Let's express 750 decigrams, dg, into grams. Let's analyze, calculate, and evaluate. The knowns and unknowns, so our desired conversion is decigrams to grams, and then we'll multiply the given mass by the proper conversion factor. So we know that our mass is 750 decigrams, And we know that there's per each gram, there will be 10 decigrams in 1 gram. And the unknowns is then finding that mass in grams. So let's set up our problem solving for the unknown using the relationship of 1 gram is equal to 10 decigrams. Let's write the conversion factor and solve for the mass in grams. We have 750 decigrams and we want to multiply by our conversion factor, 1 gram over 10 decigrams. We know that our units will cancel out. We'll do 750 divided by 10 and we get 75 grams. The result makes sense because the unit gram represents the larger mass than the unit decigram, so it makes sense that the number of grams will be less than our number of decigrams, and the answer has the correct unit and the correct number of significant figures. Moving back to this question, if you are following my Module 7 material, I posted a video on how to do these conversion problems using the King Henry likes to drink chocolate milk and just moving the decimal place that way. So if it helps you to set up it this way to solve with the conversion factor, or with problems like this, you can set up your King Henry drinks chocolate milk, setup, and then you can move the decimal point to the right or the left so many digits. Just keep that in mind and review that YouTube video on solving metric problems if that helps you too. Using density as a conversion factor. And as we're going through this, I'm just going to jump ahead. I'm going to go back to using density as the conversion factor. Because I realized I posted a worksheet talking about moles and molecules, and we're not quite there yet. I still want you to work through that worksheet and submit it with the answer key, but keep in mind that that material might not be seen on this test. More these sample type problems will be. So using density as a conversion factor, what is the volume of a pure silver coin that has a mass of 14 grams and the density of silver, abbreviated AG in the periodic table of elements, is 10.5 grams per centimeter cubed. So let's go through this sample problem together as well. Density can be used to write two conversion factors, and to figure out which one you need, consider the units of your given quantity and the units you need to answer. So we'll talk about that now. So let's list our knowns and unknowns. You need to convert the mass of the coin into a corresponding volume, and the density gives you the following relationship between volume and mass. So 1 centimeter cubed of silver is equal to 10.5 grams of silver. Multiply the given mass by that proper conversion factor to yield an answer in centimeters cubed, and we'll go through what this is. So the knowns, we have a mass of 14 grams, and the density of silver is 10.5 grams per centimeters cubed. So we're going to multiply the given mass by that conversion factor to give us an answer in centimeters cubed, because we want to know the volume of a coin in centimeters cubed. So let's set up our problem. Using the relationship, our conversion factor of 1 centimeter cubed of silver is equal to 10.5 grams of silver. We'll write the correct conversion factor and solve for volume in centimeters cubed. So we have 14 grams of silver, and we're going to multiply by our conversion factor, making sure that the gram silver will be on the denominator. So there's our conversion factor, 1 centimeter cubed of silver over 10.5 grams of silver. Noticing that the unit gram is on the denominator and the unknown is in the numerator. So that's our grams of silver can cancel each other out. And we're left, if we take 14 divided by 10.5, we will get 1.3 centimeters cubed. We just want two significant figures. Does the result make sense? Because the mass of 10.5 grams of silver has a volume of 1 centimeters, it makes sense that 14 grams of silver should have a volume slightly larger than 1 centimeter. So that does make sense. Now let's talk a little bit about multi-step problems. When converting between some units, you may need to use more than one conversion factor, which makes it a little more fun and interesting. So let's convert between metric units Let's go through this sample problem. The diameter of a sewing needle is very small. As you know, it's 0.073 centimeters. What is the diameter in micrometers? Let's analyze, calculate, and evaluate. Let's list our knowns and unknowns. The desired conversion is centimeters to micrometers, and this problem can be solved in a two-step conversion because we need to first change centimeters to meters, and then we'll change meters to micrometers. So those are our two steps: centimeters to meters, and then meters to micrometers. The known is the length, the diameter of the sewing needle, 0.073 centimeters. And then we need to know our conversions. We know there are 100 centimeters in 1 meter, and we know that 1 meter is equal to 10 to the 6th micrometers, which is 1 and then 6 zeros. So it's 1 million micrometers. And the unknowns are be solving for the length in micrometers. Using the relationship 100 centimeters to a meter and 1 meter to 10 to the 6 micrometers, we can write the correct conversion factors and solve for the length in micrometers. So we have 0.073 times our first conversion factor. So we'll want to pick the one with centimeters, making sure centimeters is in the denominator, so these can cancel out. Then we'll multiply by our next conversion factor, 10 to the 6 micrometers per meter, making sure the meter is in the denominator. So now our meters can cancel out so that we will be left with our micrometer. Making sure, remember, 10 to the 6 is 1 plus 6 zeros. So keep that in mind. And this is where we'll get our answer. We'll take 0.073 times 10 to the 6 divided by 100, and we're left with 7.3 times 10 to the 2nd micrometers. Does the result make sense? Because a micrometer is a much smaller unit than a centimeter, we should have a very large number, and the units have canceled correctly, and the answer has the correct number of significant figures. We just want 2 significant figures. I think we have maybe one more sample problem. Let's convert ratios of units. So we have the density of manganese, Mn, as a metal, is 7.21 grams per centimeters cubed. What is the density of manganese expressed in units of kilograms per meters cubed? So now we have to convert ratios of units, even more fun and exciting. So let's list our knowns and unknowns. So we want to convert grams per centimeters cubed to kilograms per meters cubed. And the mass unit in the numerator must be changed from grams to kilograms. How are we going to do that? And in the denominator, we need the volume unit must be changed from centimeters cubed to meters cubed. How are we going to do this? Well, let's first list our knowns. We know that the density of manganese is 7.21 grams per centimeter cubed. We know that 1,000 grams is equal to 1 kilogram. That's the conversion in our numerator, grams to kilograms. And we know the conversion rate in our denominator, centimeters to meters, is 100 centimeters is equal to 1 meter. And again, solving for the unknown, we're trying to figure out the density of manganese in kilograms per meters cubed. So let's solve for the unknown, multiplying the known density by our correct conversion factors. So here's the known density, 7.21 grams per centimeter cubed. We are going to multiply by our conversion factors. So let's first multiply, getting rid of grams. 1 kilogram is equal to 1,000 grams, and our grams will cancel out. Now let's get our kilograms out of there. So let's get our centimeters out of there first. So now we're going to use our centimeters cubed, but notice when we use our 100 centimeters per 1 meter, because the centimeters is cubed, we're going to have to cube our conversion. So that will cancel out our centimeters cubed. So we are left with then what we want. We want to be left with kilograms per meter cubed, but just remember that in this conversion factor, we had to cube the conversion factor. So we'll take 100 cubed divided by 1 cubed. So we'll take 7.21 times 100 cubed divided by 1,000. And then all the units cancel out, and we're left with the units we want, kilograms per meter cubed. Does the result make sense? Because the physical size of the volume unit, a meter cubed, is so much larger than centimeters cubed. The calculated value of the density should be larger than the given value, even though the mass unit is larger. All the units cancel and the conversion factors are correct, and the answer has the correct ratio of units. So that is the end of section 3.3. Thank you for listening. As usual, if you guys have any questions, please let me know, and God bless your studies this week.